Good morning, students of the course of Theory of Distributions. Now we discuss one of the most interesting examples of a singular generalized functions, maybe beside of delta function. So delta function is also, of course, of big value for us. Yeah? This is a function which would be equal to function 1 over x in all points beside of 0. Of course, in the point of 0, there is infinity. So we cannot define this function in the point 0. But nevertheless, we would like to define some function which is everywhere 1 over x except this point. So definition, yeah. Of course, we should apply this. We shall define continuous linear functional, yes. So we should take test function or basic function. So this is function say infinity, and its support is bounded. So what does it mean that support is bounded? There exists such number. Such function is 0 outside of some of the interval of the length to r. Yeah. So now definition. To apply this generalized function to basic function, this is so-called principal value of integral. What is principal value of integral? By definition, it is limit epsilon go to 0, and here we cut singularity. So there is the point x equals 0 we took out. So integral is from minus infinity to minus epsilon, and then we took out interval minus epsilon plus epsilon, and then from epsilon to infinity. So this is formal definition. Now we would like to rewrite this definition in smarter ways that will give us the possibility to operate with this integral. And first of all, we should prove, and of course we should prove that this is well defined for any such function phi, and moreover that this is continuous linear functional. Yeah, so that if sequence phi n goes, for example, to 0 in D, then this number should go also to 0. We start with such observation that if you take function 1 over x, but in principle any odd function, we change the sign between minus x and plus x, yeah, then principal value of integral is 0. Because if we take this part of 1 over x and this part for 1 over x, they cancel each other. So this principal value is 0. What now we do? We take this principal value, which is just definition, yeah, and then we subtract 0. So this is just scalar value of function in the point 0, and this integral principal value is 0. So we get this quantity was rewritten in this form: phi x minus phi 0 divided by x dx. But in fact, this principal value integral is not already singular integral, because in fact this singularity disappears. Why? Take this difference in nominator and apply the mean value theorem. So this is the difference between arguments. So x minus 0, it is x. And here the value of derivative in the middle point between 0 and x. So it can be written in this way. So instead of this, we can write this expression. This x cancel this x, and here will be this integral. So this is now very normal integral. So no problem. So we can estimate our quantity by this integral. And now consider some sequence phi n, which is convergent in the space of test functions go to 0. What does it mean? First of all, there exists such number r that supports of all these functions are in the same interval. Support means that function is concentrated on this segment. This is closure of all points where function is non-zero. Yeah. So all functions are 0 outside of the same interval. And the second, any derivative of functions in our sequence converges to 0 uniformly on this closed interval, on this segment. So uniform convergence for any derivative. In fact, here we don't need all derivatives. We need, what does it mean, the uniform convergence, that this maximum goes to 0. But from this inequality, we can, as always, estimate integral by maximum of function on the length of interval. But length of interval, because supports of all functions are here, is 2r. So this is 2r, maximum of the first derivative, and convergence in the space of basic function means that all derivatives go to 0. But in particular, we can select here k equal 1. Yeah, so this is go to 0. So this map phi into this quantity is continuous. Yes, we proved. So and linear on the space of basic functions. So this is element of those space. So this is generalized function. What we also proved, and what we shall use later in the lecture on Sahotsky formulas, we prove such representation that this integral, that we first defined it as principal value just, it was definition just principal value of this. So this was this limit. Then we rewrote this as principal value of this. But then we thought that in fact this is usual integral because there is no more singularity, it's constant, yeah? So we proved such a formula that this integral is in fact, this generalized function is in fact act as such integral, where r is the boundary of the support of this function. So for any test function, there exists interval and it's 0 outside of it. So we can represent this function, this generalized function acting to phi as this integral. So integral from minus r to r, phi x minus phi 0 divided by x dx, if support phi is in this interval. So this was very short lecture, but it's useful for the further lectures. Yes.